By the way, just a reminder, if you have any missing quarter 3 work that needs to get done like today, so I can calculate the grades and put them in quarter 3. So, any questions about that? Okay, cool. All right, so this is just a bit of a fun little graphic that I found. It's kind of neat. And there's one caveat. That N should not be a capital N. It should be a small n. But anyway, so remember, Boyle's law is PV equals K, pressure and volume. If you try to do the combined law, which is PV over T equals a K, and you don't have one of those, you just don't use it. It's like, hey, there's no temperature, there's only pressure and volume. They just don't use it. Just use Boyle's law. So we got Boyle's law, which is PV equals K. And then we got Charles' law, which is V over T equals a K. And the one that you just learned about yesterday is D-Lussac's law, which is P over T equals K. And then when you take Avogadro's number and you basically pretend that there's moles in here, then you get your Pivner. PV equals N RT. There's an R in here. It's a gas constant. Okay, so tomorrow we're going to be collecting gas over water. We're going to do what's called water displacement.
How do you get a gas?
Over water? So imagine you're swimming and somebody puts a bowl over you when you fart and they collect it. We're going to do that.
Okay.
In a small scale.
Did I fart?
Yes. So when you collect water over, when you collect gas over water, there's always going to be a little bit of vapor in your gas. All gases, or all liquids, exert a tiny amount of vapor pressure.
Yo, shut up.
All liquids exert a tiny amount of vapor pressure. Remember that little chunk of the distribution? Remember we had the distribution and it was like energy and then number or percent, and it went like that. And I said, how come even though the water's not at boiling, it'll actually evaporate? And we learned that there's this tiny little section right there that has enough energy to get into the gas phase. Well, that tiny little section is what creates a vapor pressure. So in vapor pressure, we have liquid molecules exerting pressure to become gases. And if you have higher temperatures, this distribution shifts over and you have higher vapor pressure because you have more molecules pushing into the gas phase. And eventually it gets so hot it boils, then you have very high vapor pressure. So when we collect gas over water, there's always going to be a little bit of vapor, of water vapor in the gas, unless we remove it and make it dry gas. So it's kind of up to us whether or not we actually want to pay attention to it. And here's how this works. In chemistry 1, we ignore the additional vapor pressure in most cases when we're doing labs, because it's a small amount. Like of 1 atmosphere of pressure, it's like 0.05 atmospheres of pressure. So we usually just ignore it, usually. But there is a question where we can't. But in labs, we're just going to ignore it. Okay? So it's actually really, really simple. If a container has 1 atmosphere of mixture of gases, it's an unknown gas, an unknown amount of H2, and 0.15 atmospheres, what's the pressure due to just hydrogen? If the whole thing is 1, and water vapor is 0.15, what's the pressure due to just hydrogen? 0.85. Exactly. It's just 0.85. It's whatever's left. Because if we treat all gases, including water vapor, as ideal, then it's easy to just look at their proportions. If there's only 2 gases, hydrogen and water is 0.15, then hydrogen is 0.85. Make sense? Questions? Okay, if this makes sense to you, give me a thumbs up. Okay, we don't have a lot to talk about, but what we do need to talk about, we really should understand before we move forward. If you have any questions, wave your hand around. Okay, so this idea that portions of gases behave in their proportionality is called Dalton's law of partial pressures. And it basically means this. If you have 3 gases in equal proportions, and you have 1 liter of gas, then what's the volume of each gas? I'll say it again. If you have 3 gases in equal proportions, same amount, and the whole thing makes up 1 liter, what's the volume equivalent? What's the volume of each gas?
0.33.
Yeah, 0.33, right? So if you had 3 gases and they made up 1 atmosphere of pressure, what's the pressure of each gas? 0.33 atmospheres. Huh? And again, it all comes back to treating all gases as ideal. So that's basically Dalton's law of partial pressures. It says that we can separate gases based on their proportion. So in our atmosphere, oxygen is 21%. If we have a sample of gas at 1 atmosphere, what does the pressure do to just oxygen? 0.21, exactly. 21% of the 1 atmosphere. And what's the pressure do to just nitrogen?
79.
78%. Good, yeah. Do you remember nitrogen 78%? Yeah. So nitrogen is 78% of our air. So if we have 1 atmosphere, we have 0.78 atmospheres of nitrogen. Eh?
Yeah, that's all right.
Okay. Not terribly complicated. It's just one of those things. So then if we basically say, all right, what if we had a mole of gas? Well, if you had 1 mole of air, how many moles of oxygen do we have? Yeah, 0.21. Okay. And how many moles of nitrogen do we have? 0.78. Okay. That's Dalton's law. It basically says if we treat everything as ideal, which we do, then the proportions of pressures is equal to proportions of volumes, equal proportion of moles. Okay, if you're comfortable with that, give me a thumbs up. If you want to talk about it some more, wave your hand around. No? Okay. Now we're going to draw a big bow and come right back to where we started and talk about kinetic energy. If you remember, we said temperature is a measure of what?
Average kinetic energy.
Average kinetic energy. So temperature is a measure of average kinetic energy of particles. It's not heat, it's movement. When you stick a thermometer in your mouth, you're really measuring the molecules, how fast they're slamming into the thermometer. So temperature is a measure of kinetic energy, and it's equal to 1/2 mv squared. And any sample of matter at the same temperature has the same 1/2 mv squared. And I think the analogy I asked you was, can a car have the same killing power as a truck? And you responded, sure, as long as the car is moving fast enough. Well, you can have 2 samples of gas, and classically we use nitrogen, because nitrogen's in the air, and oxygen, because oxygen's in the air. And they both have the same 1/2 mv squared. Nitrogen has a 1/2 mv squared. Oxygen also has a 1/2 mv squared. But oxygen's more massive. So it has 1/2 m v squared. Okay, so the 1/2 mv squareds are the same, but since oxygen is a little more massive, it has to be moving a little bit slower. That is Graham's law. The same temperature, the kinetic energy of one gas equals the kinetic energy of the other gas, so they have the same 1/2 mv squared, so you can say the 1/2 mv squared equals the 1/2 mv squared.
Mass, the M is the mass.
M is mass.
And the V is the velocity.
Yes.
Which is the kinetic energy.
And since we basically are treating all gases as ideal, Avogadro's law, we can substitute in, listen carefully, the molar mass for mass. Because we're treating all gases as ideal.
And then they'll just give you like the velocity.
Yep. Now, if you remember, I mentioned that velocity is speed with a direction. This is in a single dimension. Have you ever heard of the word effusion before? Effusion. Okay, you probably heard the word, guys, answer yourself. You probably heard the word diffusion. Well, diffusion is in all 3 dimensions. So gas can diffuse through the room in all 3 dimensions, X, Y, and Z. Effusion is in 1 dimension.
Like X.
Like X, exactly. So when Otis turns this way and farts, the gas has to effuse before it diffuses through the room. Make sense? So effusion is a single dimension, usually through some surface area. Diffusion is in all 3. Does that make sense?
Yeah.
And the reason we use effusion is because the math is easier. Diffusion is a little more complicated. There's like cubes and stuff. So we don't care about that. We're just going to deal with effusion.
Got it.
Ready to do some practice?
Sure.
Okay, before we do some practice, if you have any questions, wave your hand around. Okay. Ooh, wow. So consider this. By how much does a gas sample's energy change if its temperature doubles? Don't answer it out loud. Ask your neighbor. See if your neighbor. Discuss it with your neighbor. How much does the energy change if its temperature doubles?
It increases by
Make sure you need to throw up those 4s. Bro, literally is growing is 4. He's turning it.
Okay.
Look at the right side of it.
All right. With a show of fingers, 0 meaning it doesn't change at all, 1 doesn't change at all, 2 it doubles, 3 it triples, and 4 it quadruples. How much does it change? If the temperature doubles, the energy changes by how much? 2, 0, 4, 4, 4, 4, 4, 1, 4, 4. It doubles.
Dang it. Really, that's all you're
Because temperature is a measure of energy. If you double temperature, you double kinetic energy. Mass and velocity. Okay. Am I being clear? That's a test question, by the way. You know what's another test question? This one. By how much does a gas sample's energy change if its speed doubles?
There we go.
There we go. Think about this one and chat with your neighbor on this one.
Wait.
Yeah.
One of them's gonna be 4 eventually. 4.
Just keep answering 4. Eventually you get it right.
I think this one's 4.
How much do you have?
Okay. So with a show of fingers, meaning like it doesn't change, it doubles, it quadruples. What do you got? If you double the speed, how much does the energy change?
4.
4, 2, 4, 4. Some 2s. It quadruples.
Yes.
Yeah, because if your speed doubles, it's double squared. So the energy would quadruple because it's double squared. Yeah? Can you see it in the equation?
Yeah.
Questions? Okay, if you're comfortable with this, give me a thumbs up. All right, now let's rub some algebra on it. With oxygen is traveling at 450 meters per second right now, how fast is nitrogen traveling?
A little bit faster.
A little bit faster? Well, how much? How fast is it going? So this is what we do. We say, all right, nitrogen, it is 1/2. What's molar mass of nitrogen?
14.
Probably 28. Probably
28, because it's N2. Remember, N doesn't exist. N2 does. So 28. And we want to know how fast it's going, V squared. And we are comparing it to oxygen,
O2.
which is O2.
Which is probably
Oxygen is 1/2. Now, what's oxygen's molar mass? 32.
That's O2.
And its speed is 450 squared. So you got a bunch of numbers and only one variable. How fast is nitrogen going?
481
equals
Let everybody else catch up with you.
6, 7 miles an hour.
Do some math.
1/2 times.
You only have one variable in this whole equation.
1/2 times. So it's 16 equals 14. Oh, times 5.
And it's a matter of checking your context. Realize that nitrogen is smaller, so it should go faster.
Wait, how do you do square?
On your calculator,
Yeah.
just multiply it twice. And as far as getting the square root, raise it to the 1/2 power, or use the square root button. That's sitting hanging out above your parentheses. Yeah. Holding on. I don't want to cancel that learning experience.
The gas is speed doubles the gas energy.
Wait, how do you say square root?
The square root key is hanging out over your parentheses. Just hit square root answer. And if you want to impress your math teacher, you can also raise something to a 1/2 power. It's the same as square root. And you take a cube root, raise it to the 1/3 power. Always fun to impress your math teachers.
Man, that gas is hard.
And again, with context, realize nitrogen is a smaller molecule, so it should be going faster. How much faster? That's up to you to find out.
Probably. Wait.
Waiting. Take another 10 seconds.
I know, I'm already.
1/2. By the way, when you're actually putting this calculator, you can kill the 1/2 on both sides. It's on both sides.
Yeah.
So you got 32 times 40, or sorry, times 440. 32 times 450 times 450 divided by 28. Square root the answer.
Yeah.
Oh, I did get it right.
How big be it? 481?
That's what I got
Sounds good
too.
to me.
But that's
481 meters per second. And to check our work, we can realize nitrogen is smaller. It should be going faster.
But that's
481 is more than 450. Yeah.
I put 450 points.
I get it right. Oh, I'm on a retarded.
Uno más?
So I got the answer somewhere.
Any questions before we do one more?
I thought this was easy.
Uno más. If that's the case, that tiny 1/2 of 1% of argon that's chilling out down here, how fast is it going?
Oh, pretty stinking fast.
Argon is more massive than oxygen.
Pretty freaking slow then.
Pretty freaking slow, right? So how fast is argon moving?
Let me check. I got you. Slower than oxygen. What's he?
Argon is 39.9.
We're gonna do 40.
Let's do 40.
Round the numbers.
I got 160.
I'm gonna kill you.
Bro, you keep pointing. I got 402.
Incorrect.
And again, by context, argon is more massive than oxygen, so it should be going slower.
It's 402.
402.
You say so? 402?
I got 402.
All right.
402.5.
I actually got 402.4922359.
402 meters per second. Sound good?
It's kind of stuff when you do
Okay.
it, boy.
There's a question on your worksheet you're going to be doing here in about 10 minutes, and it says a certain gas is going 3 times faster than another gas.
Really fast.
Do not be intimidated that they didn't give you a number. You just basically say, oh, if it's going 3 times faster, I'm going to make that gas 10 and make the other gas what?
30.
30,
Whoa.
right?
Yes.
Easy. So, yeah, if an unknown gas is moving 2 times slower than oxygen, what must be its molar mass?
32 times 2. 64.
2 times slower.
No, divide that too. Maybe 16.
Slower is more mass.
Why don't you figure it out?
Wait.
Slower is more mass, but speed doubles. It's so times 4.
Don't Okay, don't try to do the math in your head. Say
128.
oxygen is fine. Do it in your head. You say oxygen is going 10, and that means the unknown gas must be going
20.
slower.
Slower.
5. Okay, that makes sense.
Yeah.
And yeah, it's going to be one.
Wait,
It's going to be
so
4 times.
What's
So
its molar mass?
it's going to be 4 times. It's 120.
Oh, 120.
Yeah.
Boom, 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 boom.
So sometimes,
Guesses.
sometimes even a blind dog gets a bone. But
No,
anyway, if you get that kind of question, just put a number in and say, all right, I'm going to make that number 100, so it's twice as fast. I'm going to make that number 200.
Yeah, what you want to do. Look, if speed doubles, then if speed doubles and gas samples energy quadruples, and it's bigger molar mass, it has to be.
That is true. I should to confuse Leslie, I should have been like 2.95 or something, or 2.61. Anyway, any questions before you work on your own?
No.
All right, off you go.
That was a good snack. Every once in a while. Do you know what those happen, sir?
I do not know.